Morning, everyone. So welcome to our CW seminar this week. And it's our pleasure this week we have Dr. Edoardo Borgomeo. Sorry if I mispronounced. So from Cambridge University, and to give us this talk, a very interesting talk about this keeping up with uncertainty, water resource engineering for climate change adaptations. So Edoardo, he's now working at the University of Cambridge. Before he joined Cambridge University, he also worked with the World Bank and also FAO, so on various projects, and so he got extensive experience on this water adaptation resources for the climate change and topics. So let's welcome him to give us talk today.
Thank you. Thanks, Albert. Thanks, Guantao, for the invite, and it's great to be here and nice to see everyone. So I came back to academia last year after about 10 years working for international organizations. So what you'll see in this presentation is a bit of a medley, a bit of a mix of ideas that I've kind of brought from my water policy experience, as well as some of my previous research work. And then finally, what I'll show is also my kind of plans for future research. And I think for me, it's a terrific opportunity to come here to Exeter, where there are lots of people thinking about water systems. And it's really a great opportunity for me also to receive your feedback and further ideas, especially for the final part of the presentation. So four things that I'll be discussing. First, the diagnostic of global water challenges. Then a second part of the presentation is on why we need to rethink the way in which we do water engineering, my past research streams and some example applications of my previous work, and then finally what I plan to do moving forward. So I think you've heard this before. We can synthesize the global water crisis using this interesting framework of too little, too dirty, too much, and less predictable water. Too little refers to water scarcity, too dirty refers to issues of water quality and pollution, too much refers to issues of flooding, and then finally less predictable under climate change. We know that the hydrological cycle is changing, and we expect the predictability of water resources to be more difficult to constrain. I think you've seen this before, and in water policy, when you go out of universities, you typically hear this framing quite a lot. It's a very efficient and intuitive way of framing global water issues. But the question is, how did we get here? What is the diagnostic that we can suggest to understand the current global water crisis? And I like to think of the causes of the global water crisis as paradoxes. And so I introduce here three types of paradoxes. So as you know, paradoxes are things that are unintuitive. We don't expect them. We do something, and paradoxically, we do something to get a result, but paradoxically, we get the opposite result. So I really think that with water management, we're faced with a number of paradoxes, and I describe here three paradoxes. The first one is the paradox of value, the second one is the paradox of supply, and the third one is the paradox of efficiency. These paradoxes are very important for anyone who is training to become a water systems engineer, or anyone that wants to work on water policy globally. So if we think about the first one, it's the paradox of value. It's interesting because, of course, there is no argument politically that water is precious, water is life, but then it's very difficult to understand the economics of water. What is the cost of water? What is the value of water? There is lots of discourse on we need to value water, but then there is very little clarity on how you price water, how economics of water work. And a clear example of this is the fact that, people in this university work a lot on this. This is some data on leakage levels in urban water systems around the world. You see the UK, you see my home country. In Italy, on average, we waste 40% of the water is unaccounted for in our system. This is an outcome that arises from the paradox of value, the fact that we cannot yet have a very clear understanding of the economics of water. But if you speak with economists, then they cite Adam Smith, The Wealth of Nations. This is a very famous passage where Adam Smith discusses why it is difficult to value water. It is difficult to value water because water is abundant. on the contrary of diamond. So if we read I think it's very instructive to read this and constantly remind us of this paradox. Nothing is more useful than water, but it will purchase scarcely anything. Scarcely anything can be had in exchange for water. A diamond, on the contrary, has scarcely any used value, but a very great quantity of other goods may frequently be had in exchange for it. In a market economy, what dictates the value of things is their scarcity on that market, is not necessarily their intrinsic value. Therefore, water, when you're managing water, when considering engineering solutions to water issues, you constantly need to remind yourself of this paradox of value and the fact that economists often see the issues only through a lens of scarcity and marginal utility. Now I enter the other two paradoxes, which I think are even more relevant for engineering. And again, I'm being very abstract here, but then in the second part of the presentation, I'll try to ground some of these high-level ideas in more concrete examples and concepts. The second paradox is the paradox of supply. As engineers, when we're faced with demands for services, including demands for water, our typical response is to create supply, so to augment water availability to respond to that demand. But what's the effect of creating supply on the demand? Oftentimes you don't reach balance, you actually incentivize greater demand. So this is a very common problem in many parts of the world. Again, the paradox of supply arises when you're trying to, you have the demand for a service, in this case water. You try to match that demand with supply, you bring water in with water transfer, you build a desalination plant, you build a reservoir, but instead of reaching equilibrium, you're incentivizing higher demand. The first example is from irrigation. In many parts of the world, we created irrigation systems which are great, but paradoxically we incentivized production of water-thirsty crops in areas that are not climatically suitable for these crops. So rice, sugarcane, and cotton are an example of this. Economists call this paradox of water supply the moral hazard problem, in the sense that your policies are actually incentivizing people to do something which goes contrary to your policy objective. And a second example of this paradox of supply operating is the fact that in the greatest per capita water consumption in the world is observed in places which are arid, hyper-arid, very water scarce, so the Gulf countries. These countries have lots of cheap energies. They've invested, as you know, heavily on desalination to meet the demand for water. But what has that done to the demand for water? The demand for water is actually going up to the point that, again, water consumption in these places is greater than in other countries which have not invested as heavily in very expensive desalination. This is the paradox of supply at play, and this paradox of supply also is encountered when you look at flood risk management, and it's the idea of the levee effect, which some of you might have heard of, is the fact that what your policy objective is to protect land from flooding. And so what you do is you build an embankment, but paradoxically the construction of the embankment brings people closer to the hazard, increasing their exposure to the risk. And then when flooding happens, because flooding always happens, then of course the damage is far greater. This is the levee effect. It's again the paradox of supply at play. So as engineers, we need to be very careful in designing solutions which of course address the problem of managing the hydrological variability, but trying to avoid this paradoxical outcome of having invested heavily in infrastructure that actually has increased the exposure to the risk.
They have difficulty to hear you, so I hope that we can solve that. Yeah.
If you still have challenges hearing me, please pop a note in the chat and I'll see if I can just speak closer to the mic. And the third paradox is the paradox of efficiency, and then I'll stop talking about abstract concepts to be a bit more concrete. Let me see if I lost. So the third paradox is the paradox of efficiency, and this relates to the interest that as engineers we always have on improving efficiency of utilization of resources. The classical example is irrigation. You know, agriculture is the largest consumer of water globally. the classical response to the fact that agriculture uses lots of water is to say, agriculture, why don't you improve the efficiency with which you use these water resources? How do you improve efficiency? You equip irrigated areas with efficient technologies, such as drip irrigation. This is great, it's a bit expensive, but it's a great idea. Yeah, these technologies,
audio sound from there.
yeah, these technologies they do use less water per crop or per hectare, but they also oftentimes lead to unintended paradoxical consequences. And what I'm showing here is work done by Dionysios Perez Blanco at the University of Salamanca. They did a systematic review of interventions to increase water use efficiency through modern irrigation technology, so drip irrigation. And what did they find? They found that in most places, actually, the result was not reduced water consumption, but actually increased water consumption. So the triangles, the red triangles, are places where water consumption went up after policymakers installed water-saving technologies for irrigation. And only in a few places, the green ones, the green triangles, you see that actually water consumption went down, which was the stated policy objective. What's the reason for this paradox of efficiency? Is the fact that actually when you give people an irrigation technology to save water, they might end up using that saved water to irrigate even a larger crop area. So then that defeats the purpose of your intervention. Or they might say, oh, I have drip irrigation, which is a great, very precise technology, so I'm going to plant melons, which are much more water thirsty than the previous crops. So you have a range of unintended consequences from a theoretical beneficial intervention, which is improving water use efficiency. And I like to think of these three paradoxes as a way of synthesizing some of the water challenges that the world is facing. And it's just a way of trying to introduce then this idea that we need to really rethink our approach to water engineering to try to avoid these paradoxes. And by the way, this is, again, in economics, this is what they call the Jevons paradox. So the fact that improvements in energy efficiency rarely then lead to less use of the primary energy resource. So then how do we confront these three paradoxes? Of course, we need to rethink the economics of water, the governance of water, and also the engineering of water. We are here. We're in the engineering aspect, and the rest of the talk is going to discuss a few ideas that I've worked on in the past and I hope to work on in the future when it comes to rethinking the engineering of water. No problem. So the engineering of water is I think inadequate to respond to these paradoxes, respond to the challenge of climate change. It is the water planning that we do nowadays in many parts of the world is still largely deterministic, so it's based on very simple assumptions of what the future will be like, and very few options assessed to meet the demand that is projected. We typically account for uncertainty using safety factors, but we don't know if that safety factor is proportionate to the risk that the system is facing. We don't know how much more money we're paying to achieve that safety factor. Then there is the issue of linearity of water systems, and then the lack of integration. The two examples that I bring there that's from the Thames Water 2019's Water Resources Management Plan, so a bit outdated, but it's a good example of still the emphasis on deterministic projections when thinking about how much water we need to supply to our cities. And this is Mexico City, a city where I spent a fair bit of time, which is a classic example of very poor planning, linear use of water supplies. The water gets pumped up into the city with an energy cost with an energy consumption which is similar to the energy consumed by a city of 2 million people. So huge energy cost. The water is consumed in the city and then it's pumped back out of the valley, which is a clear example of how you shouldn't do things because it prevents the opportunities from circularity and reuse of water. So what can we do to rethink the toolbox of the water engineer? Here I suggest four items. Many of them will not be familiar, many of them will be already familiar to you because many of the colleagues in this department already work and promote some of these ideas. So we need to think about strategies that are robust and flexible rather than just least cost. We need to focus on things that are proportionate, interventions that are proportionate to the risks that the systems are facing. We need to analyze trade-offs. So we moved from this conceptual diagnostic of the global water crisis in these three paradoxes to now some proposals on how we should rethink water engineering approaches to confront these paradoxes and more generally to confront the challenge of climate change adaptation in the water sector. And so there are these 4 items, and as I said, many of you are familiar with some of these principles: robustness and flexibility, proportionality in the face of uncertain risks, analysis of trade-offs and outcomes, and then the importance of understanding who wins and who loses, so distributional impacts across actors in society. These are the 4 items that then I try to operationalize in my research, and so the areas of activity of the work that I do are synthesized in these 4 buckets. The first is frameworks for water policy and planning. In other words, how do you frame problems for decision makers? How do you structure objectives, alternatives, and then understand how you arrive at decisions? The second is the hydroclimatic data analysis and development. How do you develop and extract the information that's required to make water decisions? Then water system simulation and adaptation, and then stakeholder engagement and training and teaching. So these are the 4 areas of activity, and I'll go through each one of them with some examples. The first one on frameworks. Something that I'm very interested in is this idea of risk-based decision making. This is an example applied for water resources planning. You obviously, the first step is starting on problem framing with decision makers understanding objectives, alternatives, costs, and how they see the problem. And then conducting multi-objective optimization, which attempts to quantify the risk-cost trade-offs, and we'll see an example of what that means in a second. And then alongside the risk-cost trade-offs, you also consider trade-offs with other decision metrics such as robustness, so performance under worst-case outcomes, worst-case scenarios, and then you arrive at an option which is hopefully proportional to the risks that the system is facing. And then the other example is something I worked on at the World Bank, and it's the idea of trying to help decision makers think through what is water security, how do you measure it, how do you quantify, and how do you enact policies at a country scale to improve water security. And the idea there is that you start from a water endowment, how much water is there in the country, what is its variability, and then you closely look at the institutional infrastructure assets that the country has to deliver water services, mitigate water-related risks, and then manage water resources. And what non-water people really care about is this outer circle, the outcomes that society values for environment, the economy, and people. So I like to think of frameworks, and then I also like to look at hydroclimatic data to see how we can play with hydroclimatic data to extract as much information as we can for our water systems planning purposes. The first one is, of course, working with climate model output. And these are examples from the Thames River Valley of climate outputs showing the non-stationary of PET, so temperature, and then the rainfall signal here, and this idea that the distribution of these hydroclimatic variables will change over time. These are conditional on climate model uncertainty. We know that there is uncertainty. We know that we need to be careful when using climate model outputs. And so a lot of my work is also around what we call synthetic hydrology, so essentially in vitro hydrological scenario development. Rather than relying on climate models, you rely only on your historical data, and you tweak it, you extend it, you change the time series to generate droughts that have longer duration and deficit than we have experienced in the past. And I'll stop here to explain what was done here, but this is again data for the Thames River in the UK. The red dots are the historical time series of stream flow. So it's volume of water per unit of time. For this time series, we can identify drought events And you can see that there are more than 20 drought events in the historical record. And for each of these drought events, we estimate the deficit and the duration of the event. But you can see that they don't go very far in terms of deficit and duration. We haven't experienced in the historical record a drought which is longer than 24 months using this definition of drought. What we were interested in doing was extending this drought record. And how did we do it? We essentially came up with an algorithm that was capable of matching a time series with the desired drought deficit and drought duration combination. So in scenario, you generate scenarios by first defining what you'd like the scenario to be and then asking the algorithm to generate a realistic time series that matches the drought duration deficit combination, but also matches the ranges of other properties of the time series so that that time series is realistic. In this way, you can control a lot more the scenario generation exercise because you're there tweaking the knobs as opposed to the scenario generation exercise which is top-down driven by climate model output. So this is the idea of synthetic hydrology, which is clearly very useful when you want to then stress test your water systems using things that I'm sure lots of people in this room use, which are water system simulators. This is an example of one that we built for the Thames River Basin with colleagues at the University of Oxford, which contains, again, the inputs that we've discussed on this side, the synthetic swim flow or the climate model output, decision rules, how do you operate the system, and then you run this to quantify the risk of water supplies under a range of scenarios. Other models that I've worked on, I've not developed them, but I've worked on these are more integrated assessment models, such as the GCAM from the University of Maryland. The idea here is that, as we were saying at the beginning, you integrate water with other sectors to generate a more nuanced understanding of what might be happening in the future. And then the third aspect that I really emphasize in the research, and I'm sure colleagues also working on research grants do the same, is the idea, of course, of validating and engaging the knowledge with stakeholders and the next generation of engineers. So this is work done in Ethiopia, and the other picture was Uzbekistan. I just want to give some examples of putting these principles into practice, and then I'll close by discussing my current ideas for future research. So we look at 3 case studies at different scales: city, river basin, and country. In the City of London, I worked a lot with Thames Water and the Environment Agency, who actually kindly supported my PhD about 10 years ago to understand how you identify water supply investments that are proportionate to the climate risks that the city is facing. So let's no longer think in terms of safety factors, let's think in terms of proportionality of response to the risk that the system is facing. So we developed lots of hydroclimatic scenarios. We forced them through a water system simulator, and then we were able to trade off the cost of plants against the expected annual restriction cost. So this is the undesirable outcome. This is what you want to avoid in the future. To avoid this, you need to put money into the system to make sure that this risk is reduced. So each of the yellow dots is a plan. It's a combination of options over a certain period of time, 25 years in this case. And when I say options, I mean things such as desalination plants, leakage reduction, wastewater reuse, building new reservoirs. And so what we did here was to make explicit, to show decision makers this thing which is intuitive. Of course, if you want to reduce the risk of the undesirable outcome, you need to pay, but how much do you need to pay? And this then, the decision makers can use this curve to say, okay, this is the amount of risk I'm willing to take, and therefore I'll select the plan that's highlighted in red, for example. Making this explicit is very important. Why? Because in water management, zero risk does not exist. The drought will always occur, the flood will always come. So what you need to do is you need to help decision makers actually you need to help society understand the level of risk that we're willing to take. Then once you have identified your plan, you can also do a robustness test for the different options over time to see which options the optimizer is selecting and which options are robust to uncertainty. So this is a plan, which is a combination of options. We look here at these combinations over time, and we can see that certain combinations are selected more frequently by the optimizer, meaning that they're more robust to uncertainty. And in the specific case of London, this was wastewater reuse. The second example that I wanted to discuss is from Ethiopia. So we traveled to East Africa, and here the interest was in integrating an understanding of hydroclimatic variability to understanding a range of climate scenarios for East Africa with economic models. So we're interested in cascading the impacts of climate change on water, and then the impact that these water changes have on the economy. And so to do this, you need to combine hydroclimatic models, hydrological models, and models of the economy of a river basin. This river basin is called the Awash River Basin. It's kind of the most economically important river basin in Ethiopia. And what we found, in this case, we looked only at a very few scenarios because of the computational cost of the experiment. But as you would, and what we did was estimated the economic cost of scenarios that had rainfall decrease and rainfall increase. And as you would expect in an agrarian economy like Ethiopia, when you reduce rainfall, you have a decline in GDP. When more rainfall or more water is available, sectors such as agriculture, which is displayed in green here, are more benefited from this rainfall increase. The interesting thing that we did in this computational experiment was trying to look at what these two scenarios of rainfall decrease and rainfall increase meant for different groups in society. So of course this requires some simplification. It requires also a model that is capable of explicitly representing the incomes that different groups in society have depending on what the situation in the economy is. This is how these economic models function. But what we saw is essentially that under a rainfall decrease scenario, some sectors of society were going to be less impacted than others. This type of thinking is essential, I think, moving forward to understand the impact of climate change and also the impact of climate-related interventions on society. And then the third example is from work I did at the World Bank on South Sudan, which is a country displayed there, which is 3 times the size of the UK, and only has 3 hydrological stations. So if you need to do water management in a country like that, you can imagine it's extremely challenging. I don't know how many hydrological stations there are in the UK, but we're in the hundreds, and in South Sudan it's just 3. And it's 3 times the size of the UK. So how do you do hydrology there? How do you design? World Bank needs to support these countries through projects. You finance embankments, you finance design of hydrometeorological networks to fill this data gap. How do you do that? You rely, this is obviously something that you're all familiar with, you try to rely on global data sets and remote sensing. So this is some work that I did to understand essentially the recent trends in water availability at different points of the Nile River, which cuts across the country. And this was based on remote sensing data, and we can see increasing recent flood events which have plagued the country. And then this other example shows how we can use global rasters. I don't know if you're familiar with Fathom, which is a global product. It's a flood inundation product. And we used it alongside world pop data, so again, globally available open source data, to try and develop a first map of the share of population exposed to flood risk in the country. This type of stuff is, of course, best done using on-the-ground data, but when that's not available, how do you use top-down information from global models to inform a first-level understanding of flood exposure? This is what we tried to do at the World Bank, and then you use this information to begin prioritizing, in this case, counties, sub-administrative units that are more exposed to floods and which should therefore be prioritized in terms of receiving investments. Now we look at moving towards the conclusions of the presentation. I showed past work. Now kind of in a new academic job. I've been in this new academic job for just 1 year, and I'm trying to develop further research streams and ideas. And the center of the program, the research program that I'm trying to set up is really around harnessing developments in digital technology to get more from existing water infrastructure plan a new water infrastructure, especially in low-income countries, and then also improve our understanding of where we're going in terms of global water futures. And this is kind of the big picture ambition. And in terms of concrete projects and idea, the first one is around machine learning for water-related prediction, which is something that colleagues here are also working on. And the question is, how do you improve hydrological prediction in large river basins in the global south, where, as we've seen with the example of South Sudan, we have very little data? Can machine learning help? And the question is probably yes, but how? Or how do you do it? And so working with colleagues in Cambridge to study the hydrology of the Nile, which has some data, but that can be improved. So we're applying machine learning methods to generate stream flow data for the Nile River. And the first step there is actually to do some stream flow reconstruction. So there is some data, but it's patchy. Can we use machine learning to help us complete the time series, fill the gap in the stream flow time series? That's the first step then in improving our hydrological understanding of the basin. And then the next step will be, once that reconstruction has been conducted, can we improve our ability to predict what stream flow might be in the future? This is traditional hydrology, really nothing new. The interest here is to apply new machine learning methods and then apply them in countries or areas which have been less covered by the recent advances in machine learning, which have mostly focused on North America and Europe. Then the second area is, and again, this is, I think, speaks to lots of the work that's done in this department, is the kind of water futures, but thinking about water quality. In the UK and internationally, we know that there are critical needs in terms of water quality, and we also know that there is a critical window of opportunity to inform policy making. In the UK specifically, I mean, people in the department here worked on this Royal Academy of Engineering report on water quality. The public is very upset about the status of the country's water bodies, and there is also kind of an issue with the water and wastewater infrastructure having reached its lifetime, and so being in need of kind of the rehabilitation. And how do you, so there is a window of opportunity. What can we say as researchers to inform this? I think I would like to transfer some of the thinking that I've done in terms of the water supply planning, this proportionality of interventions, this explicit simulation of risks of harmful events. I would like to transfer that to the water quality domain. And so there are three specific areas. The first one is the explicit trade-off analysis of risk of harmful water quality with the cost of system improvement. The second one is stress testing under a wide range of deeply uncertain scenarios. And the final one is how do you use, again, machine learning for water quality prediction. And many of these areas are developed by colleagues in this department, so I'd be excited also to hear your views and ideas of where this could be taken. And then the final point is on water technology. Perhaps it's worth stopping here. I think places that have the best water security in the world, like Singapore or Israel, they've also invested a lot in water technology, as you know, desalination, reuse, traditional engineering. I think that's really very important, and that type of research needs to continue. And as we see here from some of this data, most of the patenting work that's done in water is for new membranes, desalination, treatment technologies, and lots of the publications in our field are also on this type of water technology development. But what we see is that the socio-economic and especially the techno-economic aspects of these water technologies are not often examined. What do I mean? I mean that in the lab we invent a new membrane, but then we don't know if that membrane can be cost-effectively scaled up globally. Or technically, do we have the materials to do that? What would it cost to then deploy a certain technology at scale and rapidly? This type of thinking, which people call techno-economic assessments, is done very commonly for energy technologies, but I don't think we do it as much for water. And so a third area that I'd like to advance in my research program is around techno-economic assessments of water and water technologies, especially desalination and reuse. And also this idea, and this is more World Bank, but this idea of regulation. When you introduce new technologies in a system, there needs to be, of course, an understanding of the technical and economic feasibility, but also the impact that this technology has on regulation. Of course, with AI, this is very obvious. Oh, everyone now is talking about how do you regulate AI, but when you introduce desalination in certain countries that are not Singapore, so that are not very advanced, in places that have far weaker water institutions, how do you make sure that that desalination is regulated properly? How do you make sure that there is the financial architecture to support the sustained and sustainable deployment of the technology? So these were the three areas, and now just to conclude, I guess what's driving my work is the need to revisit the water engineering approaches in the face of climate change, uncertainty, and sustainable development needs, how we want to do it, develop new digital technology, the data-centric approach that we've discussed also with Guang Tao, and focus on techno-economic aspects, and then finally, what I'm interested in is designing water systems in places in low-income countries where there is higher need in terms of water insecurity. Thank you.
Thank you, Edoardo. Apology for these technology issues. Any question from the audience? Yes, please.
Yeah, thank you very much for the great talk. I think that the three paradoxes. I think one of the keys with the human behavior, and lying the three the paradoxes.
Yeah.
So I wonder how your brilliant work, or in more general our work as academics, so could drive behavior changes to get them to appreciate the value, the supply, the efficiency, make drive the changes.
Yeah, no, it's a good question. So I think the first thing is, which I try to do here, is just to increase awareness of the fact that engineering interventions lead to behavioral responses, which might undermine the objective of the engineering intervention. So I mean, first we need to acknowledge the existence of human behaviors in these systems, and the fact that they're sometimes counterproductive or they undermine what we're trying to do. So I mean, that's the first starting point, increasing awareness. And then the second starting point is to then combine engineering interventions, which are very much needed, with other types of behavioral interventions that limit these paradoxical outcomes. So the example is with the paradox of irrigation efficiency. We still need to invest a lot in water use efficiency solutions, drip irrigation, lining irrigation canals, monitoring irrigation water use from space. So we need to improve a lot on that side, but we also need to impose caps on water use, or you need to, when you give a farmer drip irrigation, you also need to clearly delimit their land to avoid that then they expand irrigated land with the new water that they have saved. So you combine your engineering interventions with caps on water use. I think that's one idea. And then there are other ideas in terms of pricing waters, of course, with urban consumers, is around this idea of block tariff, for example, so the more you consume, the more you pay. But I mean, your question is kind of open. I think depending on the problem, we'll find different responses, but the most important thing is to just acknowledge that we need to have this mix of technology solution, which is always there and it's not going to go away, alongside the behavioral incentive. And I mean, the case of Singapore, and I'll conclude here, is you invest a lot in technology, treatment, reuse, but alongside that, Singapore has done a brilliant communication strategy on new water to convince people that reclaimed water is safe to use. It's kind of a national pride to drink it, etc. So yeah, we always need to have this parallel approach in water policy. Yeah.
Thank you. Other questions? Yes.
Go on. Okay. Thank you for the great presentation, and it was really nice to see your previous work again, which I'm also familiar with. So you talk about a lot of human-led engineering solutions to the systems, to looking at the water system, also like hydrological systems. But a lot of approach we're taking for looking at especially water quality is nature-based solution, also nature-led solutions. So do you think that kind of area will be also your interest to combining to the system, or?
Yeah.
Yeah.
Yeah, no, I think that's a great point. So I think especially in this kind of second area that I'd like to pursue around wastewater, identifying wastewater treatment needs and future investment plans and solutions. I think nature-based solutions have clearly a role here. So, you know, for instance, in the first area, when you're trading off this risk and then comparing the value of the ability of different approaches to cost-effectively reduce that risk, definitely. So the question is then how, obviously for water system modelers, it's sometimes difficult to model some nature-based solutions. But I mean, that's a challenge, but definitely it's something of interest. And the more we improve the way in which we model these approaches, the better the better able we'll be to convince people that they deliver the infrastructure services that we want. So.
Yeah. My question is about this slide as well. I'm really interested to know what kind of machine learning models you are using to predict the quality in the water distribution networks or in water bodies, for example. And if you can provide us with more details about what kind of data you are using, what part of the country, what kind of models you are using, how long is the prediction, what matrices, what KPIs you are predicting.
Yeah, no, it'd be great to speak to you afterwards. So this hasn't actually started. We're starting now with a PhD who is partly supported by DEFRA, the Drinking Water Inspectorate. They're giving her access to their data sets and to begin conducting some of this. So this is, as you see from that bullet, is a very broad agenda for now. And we don't have an answer yet to all of your questions, which is why it'd be good to speak to you and see if you have any guidance. I think we took a bit of time to get access to the data, which finally we have. So now we haven't actually seen the data yet. Once we're able to see the data, we'll be able also to begin identifying, trying to begin to respond to some of your questions.
Is it limited to like water distribution networks or to water bodies like waterways, rivers, lakes?
Yeah, I think initially it's only water distribution networks, but we have to, unfortunately we haven't seen the data yet, so we don't quite know. But this is kind of a direction that we would like to take. So we'll take any feedback and any suggestions.
Other questions?
What kind of machine learning you're using for hydrological predictions?
Yeah, so I don't have a slide on that,
slide.
like this.
Yeah, this one.
Yeah. So, I mean, the person who's working on this has benchmarked a range of machine learning models. And we can I can send them to you, but artificial neural network is kind of the underlying principle there. But then she has tried also other things to see how they perform at the task of stream flow filling. So this idea of filling the gaps in the time series. I can send, the paper is not written yet, but it's beginning to take form, take shape. So if you're interested, I can send you some of the preliminary results. But the idea is essentially to benchmark a range of ML approaches and see which one is best at the task. Yeah, I guess that's the standard procedure. Yeah.
Thank you.
I also have a question for this slide. I'm wondering why you choose the machine learning model to predict the stream flow, not to use a hydrological or land surface model.
Yeah, actually, that's a great question that we should always ask, right? When we're talking about machine learning in general, like why this approach rather than a rainfall runoff model? I think a few reasons. The first one is actually to see if there is better ability from machine learning approaches to give us the information that we're after in these large and complex river basins. So, I mean, that's the first reason. It was just to see there have been new developments and, long-short LSTMs, for example, for machine learning, so long-term short memory processing. So, and people there have shown that they have better performance than traditional rainfall runoff models in European catchments and in US catchments. Can we try and do the same in these African catchments? So this is essentially trying to see if these recent developments in machine learning, they also apply to these less known catchments. That's the main reason for trying to use machine learning here. So what is there any added information there? Can these actually help us break free of the limits of limited information in these basins?
Can I just follow on this?
Yeah.
So for this one, in order to do the prediction, so what kind of input you are going to provide to this machine learning?
Yeah, I think, I mean, the tradition, like what we've been providing so far is ERA 5, so gridded data on temperature, rainfall, that kind of stuff. Land use a little bit. So I mean, that's what's being provided in terms of the training data for the model, and also the limited ground observations that are available, and you actually see with the green dots in the map. And then, so this is mostly what's been provided, gridded global data on a range of hydroclimatic parameters.
And did you have historical stream flow data?
Some, for some stations, which you see there in green, we have, but they're not complete, which is why we started with the infilling process, and then we're trying to,
Just so that's for this limited ground observations, and how do you think that we can just use the machine learning model to fill this gap, or is there any need for having more different observations from different sources in order to enhance the capability?
Yeah, definitely. I mean, I'm not a machine learning expert, and I like your question because it also invites us to think about kind of parsimonious approaches to modeling.
Yeah.
Like in traditional rainfall runoff hydrology, you want to be parsimonious. You don't put more things that you need to have good performance in your model. But I understand in machine learning, sometimes the more data, the better. So perhaps, I don't know the answer to your question,
Sure.
but probably more data would be better, but when do you stop feeding the beast? I'm not sure.
Other questions? Yes.
Just want to make sure about the strong feeling model for the prediction. Is two different algorithms that you apply, or is the single model that you apply for the same?
For this?
Yes.
So this hasn't started, that's the question mark. Here is just a range of different algorithms that we're testing based on their ability to fill the gaps in the time series. Because filling the gaps in the time series was typically done using basic regression, very simple linear regression. And now we're trying to see if other ML approaches do a better job, essentially. And here we will see, but first we're collecting the data, as I was telling Albert, this gridded data, and then seeing what can be done.
More questions?
How long data do you have for this case?
Say
How long data do you have for this case study?
It depends. So, like in the Nile, you have 100 years of data, monthly data, but for just 2 stations in the basin. For some other stations, and I mean, I was mentioning South Sudan earlier, but for some other stations, you have maybe 10 years of data, then a 30-year gap, and then 5 years of data. So it's very patchy. I don't have a slide here, but in the paper it will be presented for each of the stations, how much data coverage, year coverage you have over this 100-year window. But it's not great. It's not a great data set.
Yes.
Yeah, I'm quite interested in your progress 3, which is about a memory thing.
Yes.
So you mentioned the socio-economic is really do a little in this field. So I want to just what kind of socio-economics field you will consider reaching in the future?
Thank you. It's a great question. I think a few things. The first one is, I guess what I will consider is probably listed here, but then there are other things. So what I would like to consider in relation to these desalination and wastewater reuse technologies, or wastewater treatment and reuse technologies, is the first one is the cost of these technologies, and how much would it cost, and is it feasible to scale them? What industrial processes do you need to produce that many membrane, except this type of thinking? And the second aspect is sustainability transitions applied to water technologies. This is mostly social science, but it's the idea of looking at cases such as Singapore, Saudi Arabia, where lots of these technologies have been put in place, to look back and essentially do an historical analysis to map what were the enablers that allowed these countries to do so well in deploying these technologies, or what were the barriers in the deployment of the technologies. And then the third aspect is regulation. So regulation means understanding if you're Morocco and you want to invest in desalination and wastewater reuse, can anyone say whether your current regulatory framework is actually capable of handling these technologies? Because for desalination, you need to have limits on boron. Like your drinking water quality regulation needs to be updated in light of the fact that you're putting in desalinated water into the system. So is there anyone that can go into these places and say, yes, no, you need to add this, you need to add that parameter, you need to increase your ability to monitor this variable, and so on? So this is what I would like to do. Then there are other areas in this socio-economic dimension of desalination and wastewater reuse. I wrote this paper recently, which has some additional ideas, but one is the social aspects of it. Desalination, people still think that desalination is expensive and only for very rich countries, but actually technically that's not true. So there is a social aspect to increasing awareness. How do you do that in a good way? Obviously with wastewater reuse is the same. How do you convince people that reclaimed water is safe to drink? So there is this social awareness element, and lots of research can also go into that.
Okay, I think we are running out of time. So would you please join me to thank Edoardo for his excellent talk?
Thank you.